Hello there, Mr. Sutton here, bringing you the AB Calculus 615 Extra Practice Number 3 solutions on integration with respect to the y-axis. On this problem, let's say that M is the region in the first quadrant bounded by these two lines, y equals 2x plus 3 and y equals x plus 3, and also the vertical line x equals 4. So it probably helps if we have a visual here. Let me draw this out. Here's my xy axis. Here's the line 2x plus 3. It's somewhere above the x-axis, and it's got a slope that's positive, and that's about all I'm going to do in terms of accuracy there. We also have this other line, y equals x plus 3. It's got the same y-intercept as the first line, but it's less steep, so something like this. And then we have this other line that's vertical, x equals 4, so that's somewhere over here. And this bounded region now, this must be the region M that they're talking about. Okay, so we want to know the volume of the solid generated when I revolve this region in here around the horizontal line y equals 2. So that's a line that's somewhere down here. Okay. So in order to find this volume, I'm going to need an integral. I'm going to basically be integrating some area slices. My limits of integration are just going to be the limits of this region M. So this starts at the x value 0 on the y-axis and goes till the x value 4. So we're going to have an integral from 0 to 4. But what am I going to be integrating exactly? So since I have a volume by getting a solid of revolution, that means I have to use discs or washers, donuts, or actually pancakes or donuts. So which one am I using in this case? I have this gap here between the region M and the axis of revolution. That means I'm going to have to use washers for my area slices. So I'm going to write a of x equals pi times big R squared minus little r squared. Big R, that's going to be the distance between my axis of revolution and the part of my bounded region that's further away. So to get that distance, I can just do 2x plus 3 minus 2. 2 is the y value of my horizontal line there. So that's what I'm going to be squaring, and I still have this pi out here just waiting to be applied. Now we also have little r squared. So for that, that's the distance between this closer in part of the bounded region to the axis of revolution. So that's going to be x plus 3 minus 2 squared, and I'm subtracting that and squaring all that inside a parentheses with a pi outside. I'm going to have to integrate this by hand since this was not a calculator question, so I'm going to clean this up a little bit before I do that. I'm going to basically simplify within each of these squared parentheses, and then I'll expand them using a squared plus 2ab plus b squared. So for this first parentheses, this simplifies to 2x plus 1, and if I expand that, so 2x squared is going to be 4x squared, and I still have that pi outside. Now we have that middle term, 2ab. Since this is 2x plus 1, I have to multiply the 2x and the 1 and double it. So that's 4x in the middle. And then finally, since this is 2x plus 1, I have to square the 1. That gives me a plus 1 here. All right, on to the next one, doing pretty much the same thing. So this is really x plus 1 quantity squared. That's going to be x squared, and I'm subtracting all this, so minus x squared. Normally this would be plus 2x for the middle term, but I'm subtracting, so that's minus 2x. Normally this would be plus 1, but now I'm going to be subtracting. So when I simplify and expand, this is what I end up with, and I'm going to go a little bit further. I notice that the positive and negative 1 are going to cancel, and we're also going to have, let's see, 4x squared minus x squared is 3x squared, and 4x minus 2x is just 2x. So we have a pi, we have a 3x squared, and we have a plus 2x. This is what I have to now integrate from 0 to 4. I'm going to pull the pi outside the integral, and I'm going to write pi times the integral from 0 to 4 of 3x squared plus 2x dx. Okay, so it's time to use my fundamental theorem. Let me start by taking some antiderivatives. This exponent here bumps up to a 3. Dividing by that, we've got x cubed, and note that I still have that pi outside there. This x here bumps up to a 2 for the exponent. Dividing by that, I have now 1 x squared. All of this evaluated from 0 to 4. So we have a pi, and we have all this stuff with 4 plugged in, minus all of this stuff with 0 plugged in. this 0 stuff is going away, and unfortunately we do have to simplify because we're matching a multiple choice here. So this is going to be 64 plus 16, which is 80. So altogether then, 80 pi is our final answer, which gives us choice B. On this calculator-based problem, we want to know the area of the region in the first quadrant, bounded on the left by this function and on the right by this other function. Well, since it's a calculator question, I'm going to graph these out and see what I'm actually dealing with. So this is a little bit tricky to graph out on the calculator, because if you go to y equals, really the only variable you can use is x, not y. If you graph out all of this stuff with x instead of y, you get something like the following. And we're actually going to end up using this graph a little bit later on to come up with some useful information. In fact, let me zoom in a little bit more even. So zoom 4. So these are the inverse graphs of what they actually wanted us to graph, but we see that there's definitely some bounded regions in here. To graph the real deal, though, let me go back to y equals, and I'm going to deselect those two things I graphed. But what I am going to do is I'm going to quit out, and I'm going to do second and then program to bring up my draw menu, and I'm going to choose option 8, which is draw inverse. I'm going to draw the inverse of those two things I just drew. So let me do alpha trace y1. That'll draw the inverse of that first graph. So this is the true graph of y radical y to the 4th plus 1. And now to draw the true graph of x equals 2y, let me quit out of there and do second draw again, option 8. And this time I'm going to do alpha trace y2 and press enter. So this is the true graph that I really need to be working with here. And also, while I'm at it, just back on this screen, forever after, I'm going to refer to this first one as f of y, and I'm going to refer to this other one as g of y, because it's kind of a pain saying their full names. So here's that graph that I just drew. So if I want to find the area, and they said the area in the first quadrant, so that's just this area right here. Since I'm defining these as functions of y, I need to go from bottom to top with my integral and do right minus left function. So from bottom to top, I have at the bottom the y value 0, and at the top, I don't really know what this y value is, but I need to find it. So to do that, I'm actually going to go back to my calculator. I'm going to clear out this stuff that I just had here. In fact, I'm going to go to second draw and clear draw, just so I don't have to look at it ever again. And now I'm going to go to my y equals, and I'm actually going to graph out the inverses of this stuff. My strategy here to find the y value where this intersects, if I graph the inverse of these two things and find the x value where it intersects, that's actually going to be the y value for the original graph here. So let me reselect those two graphs that I had, and I'm going to do second trace intersect. So second trace, option 5. So these are my y equals f of x graphs here. If I want to find the y value over here to the far right, I need to find the highest intersection in this graph. So if I move my little spider up to this intersection point and press enter 1, 2, 3 times, I come up with the x value about 1.3161. This corresponds to the y value right here. So setting these things equal, I see that these things equal each other at y equals 0, and this is my inverse graph that I just drew, and also at y equals this 1.3161 point here. Now I'm going to give that a special name. I'm going to call that point P, or actually value P. That's what I'm going to refer to it on this problem here ever after. And on my calculator, I'm going to quit out of this graph, and I'm actually going to store what I just came up with as alpha P, just so I don't lose it. So now I can reuse it whenever I need to. So now to actually find this area, I'm just going to take the integral from 0 to P, and that's a y value, of, I'm doing right minus left, so the rightmost function is going to be this 2y function, and they said we were bounded on the right by this, so they already told us, but we see it in the graph here that this is the rightmost function, the more positive function. So I've got g of y basically minus this f of y function. And I'm going to put a dy there because I'm integrating with respect to the y-axis. Now to actually do this on the calculator, what I'm going to do, I'm going to do math 9 for my integral. I'm going from 0 to alpha p. But in here, to do g of y minus f of y, I'm actually going to do g of x minus f of x. So I'm going to do alpha trace y2, because that's where I stored the g function, minus alpha trace y1. And you might be wondering, how can I get away with this? Because these functions were both in terms of x. I'm going to get away with it by putting a dx right here. So as long as I use the same variable here that I was using in these functions, it's just like having y's everywhere. Your calculator doesn't care if it's x's everywhere or y's everywhere. It's just a dummy variable. Your calculator treats it the same. So pressing enter, we come up with about 0.537, which gives me answer choice A. For this problem, R is the region in the first quadrant, bounded by the graph of radical x, the y-axis, and the line y equals 1. And they're telling us that region R is the base of a solid. All right, there's a whole bunch of other stuff here, but first, I feel the need to draw out this situation because they didn't give me a grapher for this one. So here's my xy axis. We're in the first quadrant, and I have the graph of radical x, which looks something like this. We have the y-axis, and we have the line y equals 1, which is going to be coming across like this. So this is the region R in here, enclosed by these three bounding curves. So now for the solid, for which this is the base, they're saying each cross-section perpendicular to the y-axis is an isosceles right triangle with the right angle on the y-axis and one leg in the xy plane. We'll analyze exactly what all of that means in a moment, but they want the volume of the solid formed by these right triangles. So essentially we have these right triangles sort of, they're perpendicular, like the bottom of them is perpendicular to the y-axis, and they're basically popping out of this region three-dimensionally, sort of like right at you. So to find the volume of really any kind of solid, we always end up integrating some kind of area slice. The area slices on this one are going to be isosceles right triangles. Now in order to do anything here, since this is perpendicular to the y-axis, we're going to have to integrate with respect to y, which means that this function they gave me up here, y equals square root of x, no good. I'm going to have to express this in terms of y instead. Knowing the distance that the curve is from the x-axis won't help me here. I'm going to need to know the distance that this curve is from the y-axis. So to do that, I'm just going to isolate x by squaring both sides, so I can rewrite this as x equals y squared. And now I have a way of figuring out how far I am from the y-axis. The x value here is giving me the horizontal distance. All right, so my area slices are going to be isosceles right triangles. So in general, I can write a of y is going to equal 1/2 base times height. But now I need to be a little more descriptive here. At some point, I need to be able to express this formula in terms of y so that I can actually use it inside an integral. So to do that, let me get a closer look at these triangles. Here's one of these triangles. They said it was an isosceles right triangle and that one of the legs was in the xy plane. So that means that these triangles coming across here, this base here is basically, no pun intended, the distance from the y-axis to this x equals y squared curve. The problem is that we don't have a way of talking about the height in terms of y just yet, but we will. Since this is an isosceles right triangle, and this is the right angle here, that means this is the hypotenuse, which means it's not one of the legs. That means that this other side, the height of the triangle, is the leg. And since in an isosceles triangle the legs were always equal, that means that the height is going to be the same distance as the base. So this height we could talk of as being just another b, which means instead of writing 1/2 base times height for the area, I could write just 1/2 base times base, or 1/2 base squared. Now we said that the base of this isosceles right triangle is just the distance from the y-axis to this curve. So instead of writing 1/2 b squared, I can now write 1/2 y squared. because y squared gives me the distance from the y-axis. So this gives me something that I can integrate. Now, before I can integrate this thing, there is one more question I have to answer, which is, what is the interval over which I'm integrating this? Since I'm integrating with respect to the y-axis, I have to go from bottom to top for my limits of integration. The bottom value here is going to be the y value 0. At the top, we have the y value 1 because this is the line y equals 1. So then my volume is going to be the integral from 0 to 1 of this area formula I just came up with for my triangles. I can rewrite this, by the way, as 1/2 y to the 4th power, just to make it a little bit easier to deal with. And don't forget we have a dy in there instead of a dx. So now I have to integrate this the old-fashioned way using my fundamental theorem. Antiderivative of this using the reverse power rule. This bumps up to an exponent of 5. Dividing by that, we have 1/10 y to the 5th evaluated from 0 to 1. So I can yank out the 1/10 here. And inside I have 1 to the 5th minus 0 to the 5th. Well, 1 to the 5th is just 1. 0 to the 5th is just 0. So this is just 1/10 times 1, or just simply 1/10, which is going to give me answer choice A. For this problem, we want to know the volume of the solid generated when the region in the first quadrant bounded by this graph and the x and y axis is revolved around the y-axis. Before I do anything else, I'm going to graph this out and get a visual of what we're looking at here. So I've just entered this into my y equals. Not really sure what my window should be, so I'm just going to do zoom 6 to get 10 in every direction. So there we go. And this is just kind of a weird thing about these graphing calculators with these, basically this is a semicircle or kind of a semi-ellipse. But these are supposed to extend down to the x-axis. So I'm just going to draw that in my little homemade diagram here. So this is what we're dealing with. We basically have the region in the first quadrant here, and we're trying to revolve this around the y-axis to form a solid. So in order to do this, I'm going to have to rewrite this function here in terms of y instead of x, because I'm integrating with respect to the y-axis, so I need everything to be a function of y. So rewriting this a little bit of a chore, I'm going to start by squaring both sides. So we have y squared equals 16 times all of this stuff in a parentheses. And then I can divide both sides by 16, and I'll just subtract 4 while I'm at it. So I have y squared over 16 minus 4 equals negative x squared. Then I'll divide everything by negative 1 and square root. So at the end of the day here, I can write x equals, and I'm actually going to name this f of y, just so I don't have to keep writing it over and over again. That's going to equal the square root of 4 minus y squared over 16. Cool. All right, so what do we do with this? Well, if we're going to find the volume, we're going to have to do a little integration, which means I'm going to need the limits of integration for this area in here. That's going to go from bottom to top. At the bottom, we clearly have 0. This thing is bounded by the x-axis, but how far up are we going? Well, if you just count the grid lines here, it looks like this is the y value 8. And if you wanted official confirmation, you could set this thing equal to 0 and actually solve it. So if you square both sides and then subtract 4 and then divide by negative 1, we end up with y squared over 16 equals positive 4. Multiply by 16, you have y squared equals 64. And then square root y equals plus or minus 8. So yeah, this is y equals 8 up here. All right, what else do we need? We need to know what we're actually integrating. So if you're doing volume, you're going to be integrating area, some kind of area slices. Since this is a solid of revolution, we're going to have either washers or disks. Now, since the axis of revolution, which is the y-axis, is one of the bounding curves here, since this area that we're revolving is flush, has no gaps against the axis of revolution, we're going to be using disks instead of washers. So I'm going to write a of y equals pi r squared. Now the radius is just going to be the distance between the axis of revolution and the other end of the bounded region, and that distance is given by this f of y function right here. If you give me a y value, I give you the x value. If you tell me how high up we are, I'll tell you how far out we're going. So I can just write this as pi times f of y squared. So bringing it all together, I can say that my volume of the solid is going to equal the integral from 0 to 8 of, well, this a of y function that I just wrote with a dy in there. And now the rest of this is going to be up to me on the calculator. To make this a cleaner process on the calculator, I'm actually going to take this f of y function and enter it in my y equals under y2. And I'm going to enter it with x instead of y because that's how my calculator works with these y equals functions. I'm going to do this off camera. So there we go. I've entered this as y2. Now I'm going to come down to y3, and this is where I'm actually going to put this a of y function. So this is going to be pi times basically f of y squared. Now since I have already all this stuff in as y2, I can just do alpha trace y2 and then just square that, and that basically does what we're doing over here. Let me quit out of there now. And to do this integral, now all I have to do is math 9, 0 to 8 for the integral. And I stored a of y as y3, so I'll do alpha trace y3. And this is how this is going to work. Even though this is supposed to be in terms of y and I put it in terms of x in my calculator, I'm going to make all this work by making my differential dx. And now my calculator does with x what this integral down here is doing with y. So press enter, and that's 67.021, which is going to give us answer choice B. For this problem, we have this R region bounded by the graph of y equals radical x minus 1, horizontal line y equals 2, and this vertical line of x equals 1. We want to know which gives the volume of the solid generated when R is revolved around the line x equals 1. So right away, something I notice on this problem is I'm revolving this around a vertical line rather than a horizontal one. So I'm basically integrating with respect to y instead of x, which means that this function here, one of my bounding curves, that's written in terms of x, I'm actually going to have to rewrite this in terms of y so that I can use this when I'm trying to figure out this revolution. So let me rewrite this by, let's see, I'm basically going to isolate x. So to do that, I have to square both sides. So this is going to be y squared. And then if I add 1 over there afterwards, y squared plus 1, that'll give me x in terms of y. The next question I need to answer, or at least one of the questions I need to answer, is what are my limits of integration going to be? To get this area, I'm going to have to integrate something. I mean, to get this volume, I'm going to have to integrate something. So I need limits of integration. They're basically going from bottom to top of this bounded region. At the bottom, we have the y value 0. At the top, we have the y value 2. So my integral is going to go from 0 to 2. All right, now that I've got that established, I also have to figure out what I'm actually integrating. Since this is a volume obtained from a solid of revolution, since we're revolving here, that means I'm going to end up with an area cross-section that's either going to be a disk or a washer, a pancake or a donut. So are we stacking pancakes or donuts in this problem? Well, the key here is I recognize that my axis of revolution, which is x equals 1, this vertical line, my bounded region is flush against this axis of revolution because the axis is one of the boundaries. So in that case, there's going to be no gaps in there, so I can use disks instead of washers. My area formula that I'm going to be integrating then, I'm going to write a of y equals pi r squared. Now I just need to identify the radius. That's going to be the distance from this axis of revolution to the other end of the boundary, and it's going to be a left-right distance because this is all x equals something in terms of y. So the distance from here to here is going to be given by y squared plus 1, this curve right here, minus 1, the x value 1. So that's what I'm going to put inside a squared parentheses, y squared plus 1 minus 1. So then I can write my volume as pi times the integral from 0 to 2 of all the rest of this stuff, y squared plus 1 minus 1, the whole thing squared, dy. So let's see here. That's going to be answer choice C. On this problem, we have this bounded region R, and the bounding curves are x equals y cubed and x equals 4y. So right away, we're thinking this is probably going to be integration with respect to the y-axis, since we have functions that are in terms of y, functions of y. So we want to know the area of R. So since we're doing integration with respect to y-axis, we have to take an integral from bottom to top. So we have y values for limits of integration, and we have to do right minus left for the stuff inside the integrand. The limits of integration in this case are just going to be the y values at which these two curves intersect. So where y cubed equals 4y. Now, if we look at the graph they've given us, it looks like that happens at 0 and 2. And if we plug in 0, 0 cubed does equal 4 times 0. So that's one of the intersection spots. And 2 cubed does equal 4 times 2. 8 equals 8. So 0 and 2 do happen to be the limits of integration. Now we need to come up with an expression for the area inside. So I'm going to have area equals the integral from 0 to 2 of, and if I'm doing right minus left, I have to do this kind of inverse line versus this minus this inverse cubic function. So I'm going to have 4y minus y cubed dy. Since I don't have a calculator available, I'm going to have to do this by hand. Antiderivative here. This bumps up to an exponent of 2. Dividing by that, we have 2y squared. Minus, this bumps up to 4 for the power. Dividing by that, we have 1/4 y to the 4th that we're subtracting. And this is all happening from 0 to 2. So I've got all of this stuff with 2 plugged in, minus all of this stuff with 0 plugged in. All the 0 stuff is just gone, so we really just have to focus on this 2 stuff. So we have 2 times 4, which is 8, minus, let's see, this is 1/4 of 16, which is 4. 8 minus 4 comes out to 4, so that's going to be choice A. On this one, we have R as the region in the first quadrant, bounded on the right by the graph of this line here, this horizontal line, and on the left by this vertical line. We want to know which of these gives an expression for the volume of the solid generated when R is revolved around the vertical line x equals 2. So I'm going to have to graph this out because I'm having trouble visualizing this. So here's my x and y axis, and the line 3/2 x minus 3. Well, that has a y-intercept of negative 3, so down here somewhere. And we're going up 1.5 basically over 1. So we're going slanted and up. And it takes actually 2 steps for me to get to the y-axis, or the x-axis rather. So we're intercepting the x-axis at 2, x equals 2, which will be important in just a moment. So here's my slanted line. Now we're bounded above by the line, horizontal line y equals 3, so that's somewhere up here. And we're bounded on the left by the vertical line x equals 2. Now I just said that this slanted line is hitting the x-axis at exactly x equals 2. So this vertical line actually intersects the slanted line right there. So our bounded region, it turns out, R, is a triangle. Now the next piece of this is that we want to revolve this region R around the vertical line x equals 2. That's this line right here. A few key features are coming out of this. One is that we're integrating with respect to y because we're going around a vertical line. So that's one thing. Another thing is that this axis of revolution is one of the boundaries of our bounded region. So that's going to tell us what kind of area cross-sections we're going to be using. Before I go any further, though, since I am going to be integrating with respect to y, that means I'm going to have to convert this curve here to something that has x equals a function of y. So I can't have y equals something with x. I need x equals something with y. So to switch that up, I'm basically just going to solve for x. So I can do that by adding 3 to the other side and then multiplying by 2/3. So I'm going to have 2/3 parentheses y plus 3 equals x. And now this is going to tell me how far from the y-axis everything on this line is if I plug in a y value. Okay, so for the area, I have a choice between disks and washers since I'm doing a solid of revolution. Now, since there is no gap between the axis of revolution and this region R, since the axis of revolution is one of the boundaries, that means I can use disks. So A of y equals pi r squared. For the radius, that's going to be the distance from the axis of revolution to the other end of the bounded region. And this is going to be a left-right distance. To get this distance, I just have to take this curve expressed in terms of y, so basically 2/3 parentheses y minus 3, and subtract this vertical line from it. So I'm going to be subtracting 2. So I have all this stuff minus 2 squared, and then we have a pi outside to mimic this formula here. Now I have to integrate this. So let's see here. On the bottom, so I'm going from bottom to top, integrating with respect to y. So on the bottom, we have the y value 0. On the top, we have the y value 3, because this is the line y equals 3 they told us. So my volume then, I have the integral from 0 to 3, and I'm going to pull this pi outside too while I'm at it. Now inside, if I wanted to, I could simplify this a little bit just to make it match these answer choices a little better. So I can distribute this 2 to the y and the 3. So that could give me 2y plus 6, and then I'd have just all of that over 3, like so. And I should be able to match one of the answer choices at this point. So one key to matching these is that I have the limits of 0 and 3. So if you look at the limits in the answer choices, that narrows it down to b and d. The only difference between those answer choices is with b, I have some stuff inside of parentheses with a square outside of it. In D, each individual part of this is being squared. So looking at what I wrote here, this matches B, not D, so I'm going with choice B. For this one, I want to know what the volume is of the solid generated when the region in the first quadrant bounded by y equals x cubed, the y-axis, and the horizontal line y equals 1 is revolved around the y-axis. Let me draw this out so I have some kind of idea what's going on. So we have the line x cubed, that's a little snake sort of looking thing like that. The y-axis is just the y-axis. The horizontal line y equals 1, well that's just a horizontal line above the x-axis, like so. So we've got this bounded region in here, and we're revolving this around the y-axis. So that means I'm integrating with respect to y, which means that this function up here, y equals x cubed, I'm going to rewrite that as x equals something with a y in it, just so I can use it when I'm doing y integration. So if I just cube root both sides, I have x equals the cube root of y. And now I have to figure out a few other things here. I know when I do volume, I have to find the integral of an area. So that means I need limits of integration. That means since we're doing y, we're going from bottom to top. So on the bottom, I've got 0. On the top, I've got y equals 1. The other thing I have to figure out is what area formula I'm actually integrating. So since I'm doing a volume of revolution, I need to choose between disks and washers. And since my bounded region is flush against the axis of revolution, which was the y-axis here, that means I can go with disks for this one, pancakes basically. There's no gap in there. So I'm going to write a of y equals pi r squared. And for the radius, that's just the distance from the y-axis, which is my axis of revolution, to this curve over here, to the other end of the bounded region. So that's just a distance of cube root of y. So I have pi times cube root of y squared. And now I have to integrate this thing. So volume is going to be integral from, let's see here, we said 0 to 1, and I'm going to pull this pi out too while I'm at it. So pi times the integral from 0 to 1 of, I'm going to rewrite this with an exponent, so this will be y to the 2/3, and then a dy. Using my reverse power rule, this bumps up to a 5/3, so we're multiplying by 3/5, and we still have this pi outside here, evaluating from 0 to 1. I'm going to pull the 3/5 out as well. So I have a 3 pi over 5 out there. And inside now, I've got 1 to the 5/3 minus 0 to the 5/3. Well, this is just basically 1 minus 0, which is just going to be 1. So we just end up then with 3 pi over 5 times 1, which is just 3 pi over 5. So that's going to be choice C. For this one, let's let R be the region between the graph of tan inverse of x, the x-axis, and the line x equals 1.5. We want the area of R. This is a no calculator problem, So I'm going to try graphing this out to kind of get my bearings on this. So here's my x and y axis. Arctan, or tan inverse, is basically the tan function but reflected over the line y equals x. So it looks kind of like this. It sort of looks like a cube root function, only it's got asymptotes, whereas the cube root function does not. But this is the basic shape. We don't really need more than just the basic shape. We also have the line x equals 1.5. That's a vertical line over here somewhere. And this region's also bounded by the x-axis. So it's this little almost triangular shaped region in here. It's not quite a triangle, but we just want the area of this region. And let's see here. So there's a couple ways of doing this. If this were just a free response problem and I wanted to find just the area here without using a specific method, since I already have this function as y equals something with an x, I would probably just use x integration and take the integral from 0 to 1.5 of, let's see here, just tan inverse, and that would do it. Unfortunately, if you look at the answer choices, they integrated with respect to y, not x. So that means I have to integrate with respect to y, which means instead of thinking about this as a left to right, top minus bottom sort of deal, I have to think of this as a limits going from bottom to top and do right minus left inside the integral. So bottom to top, well, we've got 0 on the bottom for the y value. On the top, I need to figure out what y value tan inverse intersects this line at. So I can figure that out by, first off, let me rewrite this function in terms of y. So I can just take tan of both sides to get x equals tan of y. And now that I've got that, let me set this equal to the x value 1.5. And that'll give me the y value where they intersect. So I have tan of y equals 1.5. And just solving for y, we just have to take tan inverse of both sides. So we see that y up here, this y value, is just going to be the tan inverse or the arctan of 1.5. So I have an integral from 0 to tan inverse of 1.5. That at least narrows down the answer choices to B and C. Now I have to figure out what's inside here. So I'm going to be doing basically right minus left inside the integral. So that's going to be 1.5 minus tan of y. So I have the integral then from 0 to tan inverse of 1.5 of 1.5 minus tan of y dy. And that's going to end up giving me answer choice C.